Uh, Hi, can you hear me?
Yes, sir.
Okay, fine, thank you. I think we have only two students as regularly, and I think we'll start the class. I think she will join again. Mm, you can see the screen. One second. You can see the screen, right?
Yes, sir.
Okay, fine. I think we'll start. So as of now, there are total 7 weeks has been happened, and out of 7 weeks, we have discussed the classical thermodynamics. I mean, Sir has been teaching about the classical thermodynamics. I think tomorrow, 8th week is the last week for the classical, right? From the 9th week, I think statistical will start, if I'm right.
Yes.
I think, yeah, I think from 9th week it will be statistical. And if you, I mean, in middle, if you guys can't hear my voice, just let me know, okay? Because I don't know that whether I can. I mean, I don't know whether I am audible or not. So, in middle, if my voice is breaking or something happening, just let me know. And I think, yeah, we came to the last week. I mean, last week course of classical thermodynamics, and we are talking about the basics of thermodynamics. I mean, basics of classical thermodynamics. Like, we are not going further into the advanced thermodynamics where we will derive the equations from the basic. Suppose if I give any equation, from that we will derive the Figosity equations, or like if I give any, how to say it, if I give the van der Waal equation, or say suppose the Virial equation, from there we we will derive the VLE expansion or such other things, and we are not going into that level as per the syllabus. The syllabus basically covers the basics of thermodynamics for the biological system. So we are touching all the basic concepts, and so we all know that as of now we are studied how the equation stays, and what are the important parameters for the system, like the system surroundings. And if you see thermodynamics in classical, we will talk more about extensive variables and intensive variables, and you know the difference between extensive and intensive. And once you have know the extensive and intensive variables, we will make the parameters, say suppose the temperature, pressure, number of molecules, number of moles, entropy, enthalpy, internal energy, Gibbs energy, Helmholtz energy, and these all are the properties which you can be converted intensive properties. If you have any extensive properties, as the by name says extensive, which will change with respect to the size of the system, and we can convert it to intensive once you have these properties. And basically there are four different types of laws of thermodynamics. The basic one is related with the temperature, and the first law is related with the energy is neither created nor destroyed, and the second law and third law related to the entropy. And we all know that moment of disorderness is nothing but the entropy, and from the zeroth law we can use it for the temperature calculation, temperature calibration. from where we have the Fahrenheit scale. One second. So we have we have the Fahrenheit scale, Celsius scale, and Kelvin scale. How they have developed, but they have taken the basic assumption of ideal gas situation, and from that ideal gas equation, we have seen the how Van der Waal and how the virial equation and how the Redlich-Kwong equation has came. And further, if we go, we have talked about the parameters like say suppose if you have the real gases, and real gases we have the compressibility factor, and how does the compressible factor varies between the systems, and that we have studied, and that excess properties and all we studied, and even for the eccentric factor where we use the z equal to z0 plus w z1, if you remember. And for the extensive properties like whatever the initially we have done for the closed system ideal gas, we have done for the open systems also by adding the number of moles and Gibbs energy chemical potential. And in the further slides we have seen the chemical potential usage of the chemical potential also, if I'm not wrong, and how the chemical equilibrium attains, and what is the mu I, mu I, mu x, mu l, mu g, and all, and the excess properties and the model properties I think we have studied. And we have also studied one second, yeah, residual properties, centric factor, and then we have studied the fugacity coefficient. Fugacity is the same thing for the ideal gases, if you have the ideal gas and the real gas, and how to find out the pressure difference. And then we have seen the Maxwell Jacobian and methods, and these all are there in the previous YouTube lectures. And in the last class we have discussed about the phase equilibria. I think today is also phase equilibria, Clapeyron equation, and all the things. I think today's class is also will be starts from there, and we will I will I will revisit the Clapeyron equation, and the small things about that, and how the entropy and how the mu versus T graphs changes, and why we are using the phase equilibria. And if you okay, so I think you are getting the flowchart, right? So how we are going from basics to all the things. If you have any doubts regarding this, you can raise a mail, or you can ask in the class of the particular classes. Yeah, we have also studied the molar properties, and then we have derived the each equations of like as of now what is happening, and how to calculate everything. So we'll come to these problems at the end of the class, I think. Yeah, so you can see my screen, right?
Yes, sir.
So any doubts on this graph, like how this graph came, like why the line is steepest, I mean a little bit steepest, and why this one is the highest one, and then this one? Any doubts in this, in the phase equilibria? So you have the clarity, right, how the phase equilibria diagram came? So I think there are no doubts. So basically in the phase equilibria we have three phases, which is converted into three phases, means solid, liquid, and gaseous phase. And then it is converted, and the phase equilibrium diagram is converting these three phases into two phases. You can see this line on this line, and so suppose if I pick this line, and if I pick this line, and if I pick this line on the pink line, can you tell me what is the number of phases? So just so what will be here and what will be here?
2 and 1.
Okay, so because the phase equilibrium, you need to remember that the phase equilibrium diagram, whatever you are explaining, it is we are taking the only one component system. The initially we have carried out for the only one component system. So that's why if you are taking about any system, it will be 2 minus 2, it will be 1. So you need only one variable. So it's like 3 phases is converted to the 2 phases, and we have one variable to talk about. Then the same thing for the, and this is between solid and gas, and it will be liquid and gas, and there is on liquid and gas, and there is solid and gas. And if you remember in the last classes we have discussed, so if I take about this line between solid and gas itself, so what this line says was, if you remember this, so now I am taking for the understanding, for the I'm taking this line just for the clarification. So I'm taking this line. What this line says was, at this line says the equilibrium condition. Okay, for better understanding we can take this line, this will be better, the green one. So if I take the green line, which is in the solid equilibrium line, this is the line, this will be solid and this will be liquid, and say if you have the bowl of the solid, it stays, I mean the both will be in the same condition only if they are at equilibrium. If they are not equilibrium, we know that mu liquid is less than mu solid, so that's why the solid molecules want to go into the system. So that's why you will get, suppose if this is the system, this is the one P temperature. If you increase the P little, if you increase the temperature little bit, or if you increase the pressure, the solid will dissolve into the liquid things. If it is going this side versus, if you increase more, but if it stays in the line, it says it is the equilibrium. Equilibrium means mu s equal to mu L. Okay, to occur any reaction, we need to have one should be less than others, then only the equation will occur. The equation in the sense, the transfer of molecule from one state to another state will happen only when there is a difference in the chemical equilibrium position. And then yeah, so this is the basic thing we need to understand. And once you have this, say suppose on this line, I'm talking only about the line, the solid and liquid, at this point it is alpha, say suppose it moved to some extent beta, and since they both are in the equilibrium, we know that mu alpha equal to mu beta. So then d mu alpha equal to d mu beta. So then we know that mu is nothing but, we know that, right, molar changes in the Gibbs energy is equal to mu I. So we know that alpha alpha Any doubts in this equation? How we got this equation?
Yes, sir.
Okay, fine. I'm audible, right?
Yes.
Okay, fine. So once we have this equation of, I'm recalculating the class because this week also consider the same equations, and for this, based upon these equations only, we can solve the problems which are given in the class. So first I will, that's why I'm discussing this. So dp by dt equal to, and then we know, so which is nothing but In the book, it is written like this: latent heat of vaporization and T delta V. So, any doubts in this equation? How we achieved this? And this is the basic Clapeyron equation. So, any doubts up to here? If there are no doubts, then you know that how the entropy changes from the solids to gas is liquid then solids, and then volume also same way. Any doubts in this too? So if you know this equations and you know that dp by dt uh, is nothing but delta S by delta V. So from this you can plot why the graph between solid and liquid is more steeper than liquid and gas, and this one. So any, sorry, this is not any doubts in this from how to if you want to explain, I can explain it again. How can we come from Sg Vg, I mean the values of entropy and volume? I think we already discussed in the last class also this thing. Okay, so once this is done, can somebody, if it's possible, can we make the plot for mu versus t? So we know the p versus t graph. So can anybody tell me how the mu versus t will be look like? So what are the, how can we get mu and t? What is the relation between mu and t? So I'm drawing the mnemonic diagram. So can anybody tell me what is the relation between mu and t? So I'm audible, right?
Yes, sir.
Okay. So if possible, can you get it like in the mu and t relation? Like say suppose if I given the mu and how it is converting the chemical reaction equilibrium and how it is happening. Mu equals to nothing but, here it's nothing but S dt plus Vp. It means, so if I take any graph mu of t, the graph will be like this, negative slope because of the negative symbol. So any doubts? So now we will discuss. So now if you see this, we know that so the graph will looks like, 1 second. Gas one. This is for the liquids and solids. This will be the solid region, and this will be the liquid region, and this will be the gaseous region. Why the graph came like this? You can see that Sg is very peak, so that's why du by dt will be like more of the inclined one compared to the liquid and solids. That's why the graph comes like this, and this will be the region of solids, and this will be the region of liquids, and this will be the region of gases. So this is how you can draw du by dt plot, and you can draw the same for du by dp also, because we know that it is nothing but v. You can try it. If you're not getting, then I will explain it in the next class. The du by dp plot, how it looks. We all know that gas. So you understand, right, what I'm talking about? So once we have done with this, uh, I want to make some assumptions of Clapeyron equation. So one, the coexistence curve, the lines where dp by dt equal to so if I take the ideal gas condition, assuming it is ideal gas, so then it will be equal to integration from two places, from first position to second position, dp by p equal to integration of 1 to 2 delta h by r 1 by t square dt. So this will be like p1 equal to minus 1 by t. Minus 1 by t means it will be minus 1 by t, minus 2 by t. So it will be minus 2 by t. Minus 2 by t will gives rise to 1 by t1 minus 1 by t2. If I take t1 t2 example, then it will be positive t1 minus t2 is equal to 2 delta h by r of p2 by p1. So this is the relation between the pressure versus temperature in the presence of latent heat. Any doubts in this equation?
Sir, if we integrate, it would be minus 1 by t alone, right?
Yeah, minus 1 by t. So that's so it will be n into d minus d. Yeah, sorry. Yes. Hmm. Yeah, minus 1 by t. Yes, correct.
Yeah.
If I do the differentiation, yeah, I did the differentiation. Sorry, yeah. If I do it, then it will be minus 1 by t. I think this won't be there. This won't be there. So any doubts in this equation, like the relationship between and the final equation will be of ln p equals to, with reference, say suppose with reference point, at p1 comma t1, then this will be ln p equal to delta h by rt plus c. So this is the relation versus p versus t with enthalpy. So any doubts in this concept?
No, sir.
So then you can even try to plot how the ln p and 1 by t looks. This will go in this way. Take any 3 random 4 values and try to figure out, and if you can't, then I'll explain it in the next class, the graphs. So you can try like the phase equilibria between, say suppose vapor liquid equilibria, liquid liquid equilibria, solid liquid equilibria, which is in your what do you call in your 7th week course. Basically whatever it is, suppose if you're talking about the vapor liquid equilibria, what it says was this one. And if I'm talking about the solid equilibrium, and you can take the fugicities of at these positions. So suppose 1 second. So we know that this position it will be I'm just writing for the one condition, and then it will be for the if I take the gaseous phase, and this is for the liquid phase. So it's the same thing for the liquid to liquid. It will be like xj. You can write xi also. Xi phi high liquid equal to xi, and then you can solve these equations and these equations. We will go through this solid, liquid, liquid, liquid. So once this is done, in the phase equilibrium we are talking about one component system. In the one component system, I think we discussed in the last class also, because as this class is more of vapor liquid equilibria, uh, why why we are showing much importance in the vapor liquid equilibrium thermodynamics was because it is the process which will be helpful for the distillation. When you have two molecules, to take care of the one molecule, it will be very useful. And then one component system, say suppose we have gone through from one component to what if there is inert gases, and there is A, and we have from here we have gone to so we also found the activity coefficients gamma 1 ln of gamma 1. I think if I'm not wrong, 1 second. So the formulas will be like so if I form the formulas will be like ln of gamma 1 equal to x2 square of a12 plus 2 into a21 minus a12 into x1, and ln of gamma 2 equal to x1 square by a21 plus 2 into a12 minus a21 x2, I think. So in the last class we have derived it from the internal energy concept. So any doubts in the internal energy concept in the last week we have done? Because we know that G equal to U minus Ts plus PV. So if I apply at constant temperature and pressure, then dG equal to du. So for the whole mole we got dg, and then we have done this equation using the molar properties. I think of molar properties, if I don't remember, I have to check it in the book. It is m1 bar equals to m plus x2 into dm by dx1, and m2 bar equals to m minus x1 of dm by dx2. Yeah, with respect to the x1 we have done it. So from here you remember, right? We have done the U mix where we have taken the pure component and the species. So any doubts in the derivation?
No, sir.
Okay. So then once we have done with this concept, and then we are coming to the 1 minute. We have gone to the fugacity coefficients. Yeah, we will come to the fugacity coefficients. I think the next concept of your thing is fugacity from PVT data. So once we are talking about this, we know at constant temperature. Then you also know this into VdP and T from the F saturation to F V P saturation to P dP. So it will be ln of F by F sat equal to V by RT integration of P sat by P dP. So then we have and this, I think in the class it has been mentioned that this is the pointing factor, the values which will be there inside. So then everything remaining you all know these things. I mean, if you have seen the class, P sat equal to F sat. So I'm trying to figure out. I will in the next class I will get how the this is equation has written from the. If you see at the end there is one equation, right, from the z equal to 1 plus PB by RT, where they said B is nothing but the binary mixture. We also in the last class, in the initial classes, we also discussed that 1 plus PB by RT plus CP square by RT and whatever. We are not considering the huge terms because whatever the results we are getting, it will be matchable for these equations. And for the binary mixture, so this has been written from this. They have kind of find out the coefficient. So by the next class, in the next class, I will give the for sure the derivation of this equation. Okay, from here how we got the fugacities. Okay, because in the class they said that yeah, they have used the statistical mechanics, if I remember correctly. They said the statistical mechanics, right, to obtain these values. So I will explain this derivation in the next class. I'm still figuring out how to do this derivation. So once this was done, then we have the see the liquid. So you know Rolle's law, right? In the last class we discussed. Is there any doubts in the Rolle's law? This goes from the top to down. Any doubts? Rolle's law and Dalton's law, and what is the derivation? So Dalton's law says this one, and the Rolle's law says, and then we correlated these two. So any doubts in these equations? I mean, how the correlation has happened?
No.
So once this is done, then the concept which we have is, so for degrees of freedom. So I will give you one perspective then, because if I directly says that it is there in the what do you call, how to say it, in the class tutorial also, class week's lecture also. Have you understand the concept of degrees of freedom, how it is obtained? If we given the R equations and the constraints and the story. If you want to explain, I will explain again. The degrees of freedom one.
So can you explain?
Okay, fine. So you have this equation, right? F equals to 2 minus pi phi n. Okay, this is the basic equation, right? So first we will understand how this equation come, and then we will see for the R independent equations. Say suppose forget everything, and we have, say suppose, n components. Okay, it's like Na, Nb. Don't assume that there's a number of moles, so that's why I will rewrite this equation as, okay, so now we have C components. It's like we have, say suppose if I take the box, and if I have two faces, if I do XA, XB, XC, so on, XZ. Here it will be ya, yz. So can you tell me, so now we have 2 minus the number of components are 2, faces are 2, and the number of components are 26, right? So you got my point, right? What I'm talking. So there are 26 components of different fields. So what we are going to do was here. So understand, right, how this equation came?
Yes,
This
sir.
one. Oh yeah. So now what we will do was, so first we need to understand that, okay, see, temperature and pressure are the two important variables which we need to carry out. These are the constant variables, so these are two. Okay, you need to remember this number 2. And total how many variables we have? If I say suppose we have 3 variables, xa comma xb comma xc, how many independent variables we have here? Say suppose we will go from the shortcut. So how many independent variables? If I know xa, can I find out xb?
Yes.
So it means we have 1 here. And what about here? If I know 1, can I find out the b value without knowing c? The same thing for c. Suppose you understand, right, where I'm going. If I have 3 components, here it is 2 components. We have 2 components. The independent variables are 1. I mean, if I know one value, I can find out the other value. If I have 3 components, I need to know the values of 2 to find out the last one. I mean, if I know any 2, we got the point, right? So suppose if I have c components, how many variables we need to have? You need to know. So you understand this point?
Yes.
So now we have c minus 1 variables. And how many faces we have? So we are talking about the individual variables. So suppose I am talking about xa, xb, xc. Okay, this is one phase. Okay, in one phase I will have c minus 1 components. What about the ya, yb, yc? Here also I have c minus 1 components. Say suppose I have it in the different phase, solid phase. Say suppose in the solid phase if I mention, so again I have the 3 different phase, I mean c minus 1 components. So total will be c minus 1 plus c minus 1 plus c. So it is equal to 3. So it means the number of phases you have in the system into number of components. So we have the initials, the dependent variables are, we have p c minus 1 plus 2. So any doubts in this equation?
Yes.
So this is, assume it is 1. Or now the constraints. So constraint means the limitations. So what is the basic limitation in the phase equilibrium? Is the equilibrium, right, chemical potential. So for any component it should be like mu I equals to mu I in the liquid phase should be equal to mu I in the gaseous phase equal to mu I in the solid phase. Okay, you got this point, right? What I'm trying to say, for one component I'm talking about. Any doubts in this equation?
No, sir.
So we have 3 equations, but we have 2 phases. If you remember, this is, we have only 2 equations, right? So there are 2 p minus 1 constraints for c components. So any doubts in this line? One second. Variables 2 plus p into c minus 1. Now the constraints, the basic constraint which we have is the equilibrium one, where suppose I am taking the first one, the a. So I understand this line what I have written here.
Yes, sir.
So it should be same for, so this is the basic constraint which we are following, right? I mean basic limitation or basic thumb rule, I mean basic rule to follow to be in the phase equilibrium. So now in this way we have c components here, components are c. We have the p minus 1 equations. Okay, it's not the p phases. Suppose you have three phases, we will follow on the mu. You got me right? You have only constraints of p minus 1. You have only two constraints. Any doubts in this?
No, sir.
So it means, so now the degrees of freedom will be variables, how many variables you have and what are the constraints you need to remove. So it is equal to 2 plus p into c minus 1 plus c into p minus 1. Sorry, I think it is 2 minus number of phases plus number of components. So any doubts in this equation? So from here, how we got this equation?
No doubt.
So now we have this. Now they said that you have the R independent reactions or R dependent reactions. So this is not the variable, right? This will come as a constraint. We have one more constraint adding. Okay, so we have total C components, which is dependent on the P minus 1, plus we have the R different equations. So then it will be 2 plus P into C minus 1 minus of C into. So I think yeah, I think you will get the answer from here. So you understand the concept, right? If I given how to figure out the equations, like how to get the constraints and how to get the variables.
Yes.
So this is the degrees of freedom. So once the degrees of freedom is done, I think for the assignment problems, majorly you need to understand that. I will show the question. Yeah, before going to assignments. Sorry. So before going to the assignments, we will go through the stoichiometry, bioreaction equilibrium, bioreactors. So they said that the equation goes like this. So as stoichiometry, 3c minus b minus 2a should be equal to 0. Okay, so basically what they said was the change in the number of moles of V1 equals to change in number of moles of V2 equals to, and so on. And then it is given the equation reactant. So once you have this equation reactants, they said, you know that, right? From the Gibbs energy, it is equal to sigma of NiUi. So, and you also know that, sorry, at equilibrium. So this is the first class you remember, right? If it is less than 0, then only it will go as path. If it is equal to 0, then it is at equilibrium. This path is equal to 0. Okay. If you remember, while we were talking about the mu mixture and the liquids, we have plotted the graph between the products and the reactants. So the graph basically should go like this, but it goes like this. So this is at the equilibrium position. You remember this graph, right? The products and reactants graph.
Yes, sir.
Yeah. So these are the two conditions which we already know. And then it has been written that minus SDT plus VDP plus, if I have taken the open system where we have this one, and then we know that this is nothing but SDTP plus VDP plus mu1 dn1 plus mu2 dn2, because here we have three systems A, B and C. So 3. So now we already know that dn1 by v1 u1 equals to dn2 by u2 equals to dn3 by u3. So if I mix it to all together, because we have the numbering also here, so it is dn1 by equal to dn2 by minus 1 equal to dn3 by 3. Then if I make it all in terms of the dg in terms of dni, so it will be dj equal to minus sdt plus vdp plus u1 to minus k1 by minus 2 dn1. So any doubts in this equation? And that constant t comma p, it will be mu plus mu1 plus 1 by 2 mu2 equals to 3 by 2 mu3. So which says that sigma ui mi equal to 0. So basically whatever we had studied in the previous classes for the closed system and open system, we are applying for the same bioreactor. So any doubts in the criteria for the bioreactor equilibrium? I mean the stoichiometry or these things? So I assume there are no doubts, so then we will go to the problem. Yeah. So you remember this appendix, right? You will get this from James Smith. I think I already shared with you. I think I shared it with you, right?
Yes, sir.
Yeah. So you have these equations and you have the values of critical temperature and critical pressure, and for this problem I have taken the one bit, and then say suppose, so we'll solve the basic the last year assignment question so that it will be easy for you to understand for this assignment. So can you solve this equation? We'll have 2-3 minute time. So what we'll do, from where you will get the values and all the things. So can you tell me what are the given things? Redlich-Kwong equation. They asked to find out the saturated vapor during the process using Redlich-Kwong equation, and we all know that what this asked to find the estimate the volume of the standard vapor. So for this, if you remember in our, I think in the third week class, if I'm sure, we have taken the Redlich-Kwong equation of u plus b, and we then derived the so equation, and we have come to the place of so in this equation, this is basically iteration method. Okay, iteration method means suppose, because here they are, this is for the saturated vapor. So basically what we used to do in the sense was, what we thought it was, assume some value for this and try to find out the Vn plus 1, and then what is the difference between these two, and if the difference is greater than 2%, then you need to take this as a new assume and you need to solve, then we will get V new, and if it is also greater than 2%, then you again assume it as a new assume, and you need to do further until you get the less than 2%. So you remember this thing. Hello. Hello, am I audible?
Yes, sir.
So do you remember the equation, the Redlich Kwong, and how it has done for the saturated vapor? And then we have formula for here the A is nothing but 0.42748 r square, I think r square. One second, I will make the new slide. So now we have the equation is I think this is the equation, right? I'm not wrong, yes. And we know A equal to 0.48 r square TC 2.5 divided by PC, B equal to 0.08. Any doubts in these equations? This equation, I mean, this is we got it from the Redlich-Kwong equation, because here in the question they simplifiedly mention that we need to use the Redlich-Kwong. So these are the equations. So you understand, right? Any doubts in this? So then you have from this, so they have said the benzene ring. So now we need to go to the table and you need to find out where is benzene. Yeah. So you have the critical temperatures. So the values are bar and Kelvin. So 48.98. Critical equal to 562.62 if I'm not wrong. So you understand, right, how to get these values for your even for your assignments.
Yes, sir.
Hello. So now you have the value of 42748 r square TC 245 to PC. Now R will be 8.314 joule per kilomole. Then you are doing with Kelvin. Then you are doing with bar. So now the 1 bar equal to 10 to the power 5 Pascal. So you need to remember. So now we also know that joule equal to Pascal into meter cube. So now Pascal. So what you'll get was this will get cancelled. Any doubts in this? Even for V also you'll get the same equation if you do all for all the things, because you got it right what I'm talking. Hello. Hello. So I'm audible, right? I mean, uh, I think I'm audible. If not, just let me know if I'm not audible. So from here, so what I have was equal to 0.4274, 8.314 into r square into critical temperature is of 562.2, right? Yeah, 2 into the 2.225. Sorry. So now you will get the A value and B values. So once you got the A values and B values, then we need to put it in this equation. Okay, there are two ways to. Hello, I'm audible, right? I think so. So from here, you will get A comma B, and you will substitute here. So suppose A is, and then what are the T and P are given here. The T is given is 28 degrees Celsius, and the P value given is 1.13 bar. So suppose this is known, this is known, this is known, this is known, known, unknown. So now the unknowns are VAN and VNN. So what we will do was, so initially we will assume the ideal gas condition. So where V equal to P by RT, sorry, RT by P, sorry. V equal to RT by P, and we will get some value. Say suppose we will get X value, and then we will keep this X value in Vn place, and we will figure out the Vn plus 1. If it is less than 2%, it is acceptable. Until less than 2%, you need to do it. But this is for you understood, right, how to do these questions?
Yes, sir.
So that is for the theoretical way, but for the how to say it, as this is the objective, and if you have the less time, what you can do was, so if I am talking about the Redlich-Kwong equation and the options are given, so what you will do in the assumptions was, you don't need to calculate the A and B like separately. What we should do was, you directly calculate the RT by P. So RT by P is 8.314 into, so 10 to the power 5 Pascal. So can you let me know the answer of this calculation? 8.314 into 273 plus 28 into 8.314 divided by 1.13. So can anybody got the answer? Can anybody tell me the answer? How much is the answer you got?
0.02.
Okay, 0.02, right? So it is nothing but 2 into 10 to the power minus 2. So as I said, the closest answer will be this one. If you see, the extra part will be like, so you got this as your initial guess. What you will do was, you will do the iterations, and I think you will come to the iteration. See, you will remember, right? Once you do the iteration, the values of Vn plus 1 will reduce compared to Vn, because if you see the equation here, everything will go reducing. So you will at 2.11 you will get the less than 2%. That's why you are given the 2.11%. So your closest proximity value, if you are, I mean, if it is asked in the objective part, you can do this. Otherwise, you need to do all the process. So any doubts?
Yes, sir.
So now the answer for this question is 2.11 into 10 to the power minus 11. Even you can try in the theoretical way also, like how much you are getting. If you are, I hope that you will get the same value. I think, yeah, I think you will get the same value. Yeah, you will get the same value, 2.2 into 10 to the power minus 2. And what about this one? So, so in the previous example, if you see it here, we calculated the V vapor. Remember this? We calculated the V vapor. So now we are calculating the, yeah, now we are calculating the, see, this is the previous question. This is the new question. This is question 1 and question 2. Sorry, I mixed the both. So here we calculated the V vapor and we are calculating the V liquid. So do you know the equation for the V liquid? So given temperature, pressure, Redlich-Kwong equation. So what, if you remember in the I mean in the third week, if you go and watch the third week video, you will get this one. I mean, I'm not going to solve the equation again, because so we added, if you remember, we added multiplied and divided by V into V minus B by V plus B, such that this V plus B and this is get cancelled. So we got, if you see whole equation, we made it in the function of V, and the final equation will be in the form of, yeah, this equation. You can recheck your notes also. I mean, it's in the class notes. Any doubts until now?
Yes, sir.
So for the vapor, what we have done was, for the vapor, what we have done was, we have calculated Vn equal to RT by P. For the liquids, we will consider Vn equal to B. You know, right? What is B was? We have the system with different molecules. One second, P equal to RT. Then we have, yeah. So we know that while calculating for the van der Waal and from the van der Waal or Redlich-Kwong equation, what we have done was, we have considered the this molecule as an entity, and the space occupied by this will be V minus B, if you remember, and the interaction between these two will be A by V square. You remember these two terms, right? V minus B and A by V square.
Yes, sir.
Yeah, so that's why for the liquids we are considering the liquid, the space occupied by the liquid. So that's why we are taking the, here the guess will be B. So now what you will do was, the B value whatever you are getting. So you know the formula for B, right? The B formula will be the same. So it is again benzene. So if it is benzene, we know, I think, what is the value? 48.98. So can you tell me what is the B value? So if I try to solve this, my B value will be 0.08664 into 8.314 into the temperature is 562.2 divided by 48.98. So how much you got the value?
8.268.
So
268.
8.268. So now if you calculate for the units, so R is joule per kilomole, no, Kelvin mole, sorry, Kelvin, and it is Kelvin, and it is, if you see, the units are in the bar, so divide by bar, which is 8.2. I mean, I'm doing for the dimensionless number. I mean, I'm bringing the units because here the units are in the meter cube per mole. So you can try it. Joule is nothing but Pascal into meter cube into Kelvin divided by Kelvin into mole into 10 to the power 5 Pascal. Pascal cancel, so it will be so now this will be your initial guess of Vn. Here you need to put the this Vn value as this, and you need to do the iteration, same thing for formula. But yeah, if you remember, our main goal is here was, yeah, I'll write it here itself, no issues. Yeah, if it is asked in the theoretical part, you need to do the Vn from the B analysis. You need to assume that, okay, whatever the result, you need to assume that, okay, in which units I am writing, because see, you got the 8.2 divided by bar, so now you are converting the bar into joule per bar. Kelvin into, so yeah, the answer is same, but you can think that your answer is not nearer to this one, so that you might think like, but so that's why you need to remember that you need to change the units, so that's why you will get, if it is for the objective you can do this, and sometimes it's better to recheck the values by doing the calculation also. Any doubts in this? For the objective,
Yes.
for the objective mode, you can try it. 8.958. Yeah, so can you try this one? So can they tell me how can you try to do this? So I will give the options given. We have, say, so yeah, from this question what did we found out? We found out the V vapor and the V liquid. So you can see it here. The vapor pressure is how much it is? 2.11 into 10 to the power minus 2. So the V vapor is 2.1 into 10 to the power minus 2, and the V liquid is 8.8 into 10 to the power minus 5. So if you remember in the initially we talked that V gas. You remember this equation, this condition?
Yes.
Hello. Uh, hello, hello, Netrasri. Am I audible?
Yes.
Uh, hello, Fahima.
Yes, sir, you are audible.
Yeah. Okay. Fine. You understand this condition, right? So from here also it is proved that the major difference between the gases and liquids. Uh,
Yes.
so now, yeah. So now we have here they given that the molar volume of butanol in the liquid phase, V liquid is 0.1225 into 10 to the power minus 3, and volume in the vapor phase is 8.96 into 10 to the power minus 2, and the latent heat L is equal to, so they're asking change in the, and they're given the temperature as 390 Kelvin, pressure as 5 bar. You can read the question again. 1 second, yeah. I thought the video is got Not recorded. Okay, fine. Yeah. So can you understand the question again? I'll give 2 minutes time. So from phase diagram, what is the terms which we have and what we can, how can we solve? We have delta V and the delta H is nothing but the latent heat of vaporization, and we have the temperature, pressure. So how can we solve this? I mean, what is the formula which will be suited? We can try it. I mean, you already know, right? Say suppose if I take the vapor liquid, it will be mu vapor equal to mu liquid. Then mu is nothing but minus SDT plus VDP. I mean alpha beta. So here also you'll get minus beta alpha V alpha. Here you get. So now if you do this, you will get dp by dt. Some equations you will get it, right? So you can tell me which equations, how can we solve this? Because the value should be kilopascal per Kelvin. So you are taking the values, right? I'm just making a new slides. So you understand the question, right? First thing is question understanding. Hmm. So you know the values, right? I'm just skipping to the answer. So understand the question, right? So we have delta P by delta T equal to L by T delta. Any doubts in this equation? How we got this? Hello.
So can
Yeah. So if you remember, so latent is nothing but delta H. This one, if you remember, it is fine. Want me to explain this equation? Hello. Hello. So what I will do was, I'm audible, right?
yes, sir.
So what I will do was, say suppose I am moving from one position to one position, from alpha to beta, on the curve, coexistence curve. So from equilibrium we know these conditions. So if it is not equilibrium, say if it is, say suppose mu alpha is less than mu beta, it means it won't go to this extent. It wants to come into this way only. So if it is mu beta is less than mu alpha, it will go like this. It won't stay in the coexistence curve. You should remember this. So now we know that mu is nothing but SDT plus VDP. Yes. So minus SDT plus VDP. So it is minus alpha dt plus V alpha dP equals to minus S. So now if I put, we also know that G equal to H minus Ts. So it means H alpha minus, you should remember the bar is there. Beta minus Ts beta. So it will be So now here I am putting this value, so this will become T by h beta minus h alpha divided by T into V beta, so it is nothing but delta H into T delta V. So this V is nothing but V vapor minus V liquid, because vapor is higher than the liquid. Understand how this equation came, this one?
Yes, sir.
So now you have the, you have the V liquid, V vapor on the kilojoule per kg. So you can think that this is direct question as dP by dT equal to the temperature given is 390. So the values are 8.96 into 10 to the power minus 2 minus point. So now if I take the units, kilojoule per kg, right? Yeah, kilojoule per kg. Kelvin, the volume is in meter cube per mole, I think. The asked one is in the, you can see, right? You can see my screen, right? I'm moving very. Have you noted down the values of this one? Hello, you have taken the values, right? So now if you have taken the values, now the question was asked in the form of kilopascal per Kelvin. So but we have the units in kilojoule per kg per Kelvin into meter cube per mole. If I convert this, I can send it to up kilojoule per kg into mole per Kelvin into meter cube. So in the, from the last we are seeing that 1 joule equal to 1 pascal into meter cube. So 1 pascal equal to joule per meter cube. So this is kilo, this is Kelvin. Okay, don't get confused. So now this 2 will become as kilo small k pascal divided by Kelvin. Now we have mole per kg. This I will write it as 1000 grams per mole. So we know this. So the equation is butanol. So it is butanol. It is C4H9OH. It is 4 into 12 plus 10 into 1 plus 16. So 12 4 is 48, 10, 16. 74 grams per mole. 1 mole has 74 grams. So now I am rewriting it. So now delta P by delta T equal to 542 into 392, 6 into 10 to the power minus 2 into 10 to the power minus 3 kilopascal by Kelvin into mole per kg. I am writing here it as 1000 grams, and the 1000 grams we have 74 grams per mole. So the mole will get cancelled, gram will get cancelled. We have the kilopascal per Kelvin. So can you give me the answer for this question? So so how much it will be there? I mean 0.0896 minus 0.001225 into 390 into 1000. So 2 into 70, sorry, 2 into 74 divided by 348 96 and 225. You got the value?
Yes.
How much it is? I mean, can you tell me?
0.14 now.
1.14. This will be
Nine.
kilopascal by Kelvin. So you understand, right, how we got the kilopascal and everything? So this is this one. Any doubts in this calculation, how it was done? So any doubts in that problem? So basically what we have done was, we know how to calculate the vapor, V is nothing but V vapor, and second we know how to calculate the V liquid, and then if they ask to find out the delta P by delta T, we know this is nothing but L into T into delta V. It is nothing but L into T into V vapor minus V liquid. Okay, so it may come in different questions. So for to find out the vapor, we need to know the Vn. Here the Vn is nothing but RT by P. If you know RT by P, then I mean objective wise you need to be close to this value, and for theoretically you need to do the iteration process. For the liquid, you need to know the B value. B is nothing but some 0.0, if I'm not wrong, I mean I 8664 or TCPC. The critical temperatures of, I think, pressures of the function, I mean the component which is the mixture, the component which is given, you will get it from the appendix B from James Smith. I think I have already shared the James Smith appendix B, right? I think so I don't need to share it again. If I'm not, then I will share it again. So if you have this one, then you can find out the delta V. Then the T will be given in the question, and L, latent heat of vaporization, which is nothing but the shifting from the vapor to the liquid. So there is nothing but latent heat. So then we have L by T delta V. Any questions in this? How to solve the assignment problems? And you need to remember how to change the units. Be careful while changing the units. So 1 gram is nothing but 74 point. In the case of butanol, I am writing. So you need to do for the acetaldehyde, get the acetaldehyde formula and do it molar mass. Then you will get it gram, and everything will get cancelled out. The joule per meter cube. So any doubts in this? And the degrees of freedom also. So you need to remember the F is nothing but variables minus constraints. So you need to understand that what are the variables you have. The temperature and pressure is constant, and how many phases you have, or I mean I'm not writing it, I'm writing it in the wrong way, but you should understand what I'm. So then how many compounds you can have and how many phases, and the constraints are What are the constants is nothing but the limitations or like the principles which we are following. So we need to have the p minus 1 equations for the c components, comma r independent equations. Then you need to make a formula out of this for the degrees of freedom. And then at equilibrium, you know that for the given reaction from the product to the reactants, basically if we expect that this will go like this, but in generally if you see the mu mixing, it goes like this. So the at equilibrium, because at equilibrium only, if it is in the equilibrium only, then mu I of liquid is equal to mu I of solid. So you are understanding the concepts, right? If you have any queries regarding the concept, you can ask. If you're not understanding any concepts, and in the next class I will try to figure out the fugacity coefficient, the derivation, fugacity coefficient derivation. I think the last class videos are also like full of Morgulus model, Van Laer equation, and the Wilson equation, which we derived in the class. I think the video was cut a little bit. I think still it has clarity. If it is not, then I will explain it in the next class. Is it you understand right how the Redlich crystal equation has came?
Yes.
So then how ln gamma 1 and the ln gamma 2. If you have any questions regarding the thermodynamics, you can ask. If I don't know, then I will explain it in the next class. So because after the next class, I think we will directly go to the statistical thermodynamics, where we will talk with the molecules, atoms, and all the things. I mean, we will so as of now we are considering the entity with a closed body, where temperature, pressure, volume, number one, and two. We are changing the components. Now we will have the atoms, small atoms, and how the atoms, the rotational and the translational forces, and the internal energy, how does it act. We will discuss more about that things. So I think the week 8 is the week 8 is the last week for the statistical, classical thermodynamics. So if you have any questions, you can ask. If I don't know, then maybe I will get it to you in the next class. If you have any queries, you can ask. So any queries regarding the class? Regarding thermodynamics, if you have any doubts also, if you didn't understand any concept, maybe I will brush it in the next week if you want me to explain for the classical thermodynamics. Just let me know. So if you have no doubts, so you understand the concepts, right? Just for the sake of review, like feedback session. I think I'm audible. I'm audible, right? Am I audible?
Yes, sir.
I think I can't hear. So, if you have questions, you can ask. We'll wait for another 5 minutes. So if no questions, thanks for attending the class. Thank If you have no doubts, you can leave the class. Thank you for attending the class.